With the mechanical events of the heart, they include systole first. Systole is that top number of your blood pressure that we all know. And during systole, heart contraction happens. The bottom number of our blood pressure is diastole, which is the period of heart relaxation. And when we consider the cardiac cycle, we most often think about the left side of the heart just because that's where there is higher pressure. But also, the same events are happening on the right side of the heart at the same time as well. So, the next few slides will show the individual parts of the cardiac cycle. And we're going to first start with atrial systole, which is the contraction of the top part of the heart, followed by atrial diastole, and then this is followed by the events of the ventricle. So the same events are going to happen in the ventricle, systole, and then diastole. So the cycle itself represents a series of pressure and blood volume changes. And they follow, and this is a very important part, is they follow the electrical events of the ECG. So just like with skeletal muscle, there has to be an electrical event that leads to the muscle contracting. It's the same with the heart. There has to be an electrical event. In this case, it's the intrinsic conduction system that leads to the contraction of the muscle. So the first step is ventricular filling, mid to late diastole, and during this time period the pressure is very low. And important parts of this, important events that occur during ventricular filling. So imagine at this point blood is going from the atria into the ventricle because the ventricle is filling up. So that means that the AV valves are open, the tricuspid and the bicuspid valve. So at any one point during the cardiac cycle, it's important to remember that only one set of valves can be open. So in this case, the AV valves are open, but the semilunar valves are closed. Now what leads to this is the atrial depolarization event, which begins from atrial systole. So that's the P wave. So we see the P wave, the atria depolarizes, and that leads to atrial contraction. It pushes blood in through the AV valves into the ventricle, and once the ventricle fills up, the volume that's present in the ventricle is called end diastolic volume, and diastole means filling, the filling phase. So that's the maximum amount of blood volume that will be present in the ventricle. The next thing that happens is the depolarization spreads to the ventricles. That's called the QRS wave or QRS complex. The atria finish contracting. And then at this point, the semilunar valve closes. And so for a period of time, we have all four valves closed. We have the semilunar valves closed, and we have the AV valves closed. And because of this, the ventricle can generate pressure. And as that pressure generates and rises, it causes the closing of the AV valves. So now the important thing for isovolumetric contraction to remember is that all four valves are closed. The AV valves are closed, and the semilunar valves are also closed. So the pressure in the aorta is about 120 millimeters of mercury, but what's going to happen next is that the pressure is going to increase in the ventricle so that the ventricle can contract. And those events we're going to look at in the cardiac cycle a little more closely as we see on this diagram. So there's a lot going on this diagram, so I'm going to zoom in so you can see it a little more closely. And what we want to first look at here, it's important to start with the ECG because we already know those events. And remember, the events of the ECG actually occur before the other events. So the ECG is going to be on the top of this slide here. So we have the P wave, atrial depolarization, the QRS complex, ventricular depolarization, and then the T wave, which is the ventricular repolarization. So what I want you to see first is the pressure waves, or the pressure graph here. So notice that first this pressure, which is very high, is the pressure in the aorta. The pressure in the aorta never goes below 120 millimeters of mercury. It's the highest anywhere in the body. And basically, the easy way to remember blood pressure is that it drops the further away it is from the heart. So the aorta is the first blood vessel that comes out of the heart, so it would be the highest blood pressure. The next two graphs are the atrial pressure and the ventricular pressure. And as I said, we talk about the left side of the heart just because there's a much greater change in pressure. And basically, pressure is going to be the main event that triggers blood flow or blood activity. So the P wave, the atrial depolarization, first happens. Right after that happens, there's pressure increase in the atria, so it causes the atria to contract. And as the atria contracts, blood goes into the ventricle, and this is the part called isovolumetric contraction that I showed you a couple slides ago. So just to remind you, isovolumetric contraction is number 2 on this slide. So the AV valves are closed and the SL valves are closed. The semilunar valve closed. And notice down here it says the pressure in the aorta reaches about 120 millimeters of mercury. At this point, at the end of isovolumetric contraction, the pressure in the ventricle is actually going to exceed this. So let me zoom in just a little better so that you can see here. So we can see the blue is the pressure in the left ventricle. At this point, during isovolumetric contraction, all valves are closed, so the pressure generates in the ventricle. It generates to a high enough level that it actually exceeds the pressure in the aorta. And that's the point at which the semilunar valves open. Remember, there's no point in which all 4 valves are open, but there's a point at which 2 valves are open at a time. So at this point, the pressure is going to rise above the aorta. It's pushing blood now to the entire system. So during this time period, what we see down here is the ventricular volume curve. And it's the volume of blood that's in the ventricle. And I already mentioned the end diastolic volume, abbreviated as EDV. That's the amount of blood that's present in the ventricle after it's completely filled. So during isovolumetric contraction, the volume doesn't change. It's equal volume. That's what isovolume means. At the end of that period, the semilunar valves open, and they eject blood. The amount that they eject is called the stroke volume, and that normally is about 70 milliliters of blood, but that obviously can vary quite a bit. So after the left ventricle has ejected blood, the amount that's remaining is called the end diastolic volume. And at the bottom of this figure, we can see the flow of blood and where it is. So I think it helps to start with the electrical events and think of how those lead to the pressure events. Think of the muscle actually contracting after the electrical events tell it what to do. So back to our previous slide, just to review that with you. During diastole, this would be following ventricular relaxation. The ventricles relax, and the end systolic volume is present. The end systolic volume is always going to be a much lower volume than the end diastolic volume. So the way to calculate the stroke volume is to subtract the end systolic volume from the end diastolic volume. So our next slide after the cardiac cycle is showing us where we can actually hear the heart sounds, the two heart sounds of lubbed up. And they're associated with the closing of heart valves. And if you put a stethoscope on these areas of the heart, you can hear the different ones. So for example, the first sound is the closure of the atrioventricular valves, the AV valves, at the beginning of ventricular systole. And specifically, those would be the mitral valve and the tricuspid valve. The second sound is the closure of the semilunar valves at the beginning of ventricular diastole. So this slide is showing cardiac output, and cardiac output has to do with stroke volume, and we've talked about stroke volume now and how to calculate it. It's end diastolic volume minus end systolic volume. And in order to get cardiac output, you have to multiply the heart rate times the stroke volume. And it's usually about 5 to 6 liters. And the cardiac output is the amount of blood that's pumped out by the ventricle in 1 minute. So there's a lot of factors that affect cardiac output, as you could imagine. And the main factors are what affects stroke volume and what affects heart rate. And what's really interesting is in athletes is that athletes tend to have really low resting heart rates, and they compensate for this low heart rate with a very high stroke volume. So maximal cardiac output, it may reach 35 liters per minute in trained athletes. And of course, this doesn't mean that they have 35 liters of blood in their body. It means that the blood is being pumped out of the heart much, much more efficiently because of this stroke volume.